welcome everyone. We made it to another weekend. Hallelujah. Okay. Hopefully, if you all take care over the weekend to wear your mask and to obey that social contract that you signed, I remind you that that social contract is in force even when you're off campus. Even when you're off campus. It's not like you wear a mask and distance here on campus. You do that the entire time. You're all looking great, but I'll tell you, yesterday, I'm very excited. Today is my wedding anniversary.
Oh, happy anniversary.
Yeah. How many years do you think?
25.
15, 17.
50.
6 years, 44 years.
Wow.
This poor woman has put up with me for... Well, anyway, I was out buying flowers yesterday for guys. That always works. Flowers are always good. But there in line in front of me is a woman. She's got a mask on and she doesn't have her nose covered.
Then what's the point?
That's the whole thing. The nose is the most infectious part. Why do they think they stick the swab up your nose? Because that's where it is. So I almost told her, but she got outside by the time I could. So I didn't want to bother in the parking lot. But if you don't cover your nose and your mouth, it's pretty much futile. Okay. So please try to do that while you're out there. Now, the next thing is the quizzes went great. I'm very happy about that. What we're doing now is the weekly quiz is going to be on Wednesday. If you're here, you'll take it live. If you're not here, you'll take it between 10 and 10:30 on campus. And it looks like everybody did that, so I'm very, very happy about that. Our first exam is a week from today, and it's on chapters 1, 2, and 3. There are 2 review sheets, okay? There is a Newtonian mechanics, and then there is Copernican astronomy. Make sure you have both. I still have some Copernican astronomies here, so if you're missing that, you can take one. And also, there you go. On the Newtonian mechanics, I am going to skip to catch up here. Anybody else need one? I'm going to skip the section where it says on page 2 at the top, it says science and mathematics. Where it says science and mathematics. Which one do you need? Copernicus, okay. It says my copy, but you can have it, okay. Where it says science and mathematics, we did talk about vectors and scalars. We did talk about that. A vector is something that has direction, a scalar does not. But the other stuff on calculus, analytic geometry, and deductive and inductive logic, we're going to scratch it. So at the top of page 2, where it says science and mathematics, scratch deductive and inductive logic, analytic geometry, and calculus. But vectors and scalars, we did cover. You can look them up in the textbook and the index, and you should know that a vector is directed quantity. And there are scalars, which are not directed quantities. So, we will not have a review session because all you can do is go back and review the videos. The test format will be multiple choice matching, which is really multiple choice with lots of distractors. And then I will also have an extra credit essay question. The extra credit essay question is worth up to 10% on the exam. You can raise your letter grade on the exam by 10%, and you can get partial credit for it. But it has to be an essay. If you want to know what kind of essay questions they can have, I can think of a zillion of them. Describe Newton's laws of motion, which we're getting into today. Describe Galileo's theory of, derive Tycho's theory of the universe, or describe Copernicus's theory or Aristotle's. Any of these things could be essay questions. All right. Start studying now. Start studying now. Multiple choice questions will be similar to the ones that were on the quizzes, though I might make them a little bit harder. Yes?
So then if you get 100% on the matching and you do that,
You can get 110% on the test. Oh yeah. Yes. And also, I'm going to be sending out an email on extra credit. The planetarium show for this month is out. And if you watch that show and write a 1-page to 1.5-page double-spaced report, you'll get an extra 5%. So I'll send an email out about that. So you can read the email, and the link is right there too. Also, the Folk Festival is coming up. It's going to be online. There's going to be a songwriting workshop, and I forget the performer's name, but she will be talking about a songwriting workshop on how to write protest songs. So for you people who want to get involved with the protests, protesting despite what some people think is not writing, and protesting is a good thing if you're protesting something that's worthy of protesting. And there's a lot out there worthy of protesting right now, okay? Just do it peacefully. That said, I want to start talking about Galileo. I think I hinted at him last class. And what Galileo did, I already mentioned his thought experiment, where he argued that if you had two objects and you allowed them to fall, that if you suddenly glued them together, they are not going to fall faster. So there's something not quite right about this idea that heavier objects fall faster. He realized that the problem was the air. That air resistance was influencing a falling object. He said, can I study an object but remove the influence of the air? And he figured out that if he slowed it down, instead of having the object fall straight down, if he could make a ball that was smooth enough, not easy to do. I would defy any of you to take a wooden ball and make it perfectly smooth so that there's no wobble. That is not easy to do. But let it roll down an incline rather than fall straight down. He argued that if you allowed it to roll down an incline, the essential character of the motion would not be changed, but it would be slowed down. So if you take an object falling straight down, and then you put it on an incline, and then you gradually decrease the incline from being straight up and down to a true incline. So we could start by dropping the ball straight down. Well, in that case, the incline has absolutely no influence whatsoever. But if you then lengthen the incline like so, it's going to obviously travel more slowly. And if you increase this without bound until you have a very gentle incline, you can decrease it to the point where you can time it using the clocks that were available at that time, and that means pendulum clocks. If you just try and drop it straight down, you need an electronic clock. But if you let it roll down a long incline, the essential character of the motion is unchanged. It's slowed down. And you can roll a marble, you can roll a cannonball, but they all have to be made perfectly round, no wobble. And the incline must be perfectly smooth. Not easy to do, but if you think about it, even back in the 1600s, they did know how to work with stone. They did know how to work with stone, and they could make stone very flat. Now, I don't know if he used a stone incline or wood or whatever, but in any case, somehow he got a very long, nicely smooth incline, and he rolled balls down it. The balls were very smooth and without wobble, and then he was able to use a conventional pendulum clock to record the motion of the ball. In fact, what he did is he put little gates on here. It's really cool. put little gates here, and anytime it went through the gate, it would make a snapping sound. It would make a snapping sound. And he'd be listening to the pendulum clock, and clack goes the pendulum, and he'd release the ball. And then he would arrange these gates so that they clacked in unison with the pendulum clock. So he had multiples of time coming down, and of course he could measure the distance, and he could measure how the distance changed over time. And he could make this gradual enough that he could slow it down to the point where a pendulum clock could be used. And he then graphed his results. And he found a couple of remarkable things. So when he used an incline and he graphed the motion, one question we can ask: if you park your car on an incline and pop it out of gear and just let it go, what does it do? It rolls faster and faster and faster and faster. My poor sister-in-law was sitting at her grandparents' house one time, and she saw suddenly her car rolling down the driveway, down into a 4-lane highway where it was hit by a dump truck. Boom! Slipped out of park or whatever, and it just, and she just caught it at the end, and obviously it was totaled. Okay. I mean, can you imagine that? Can you imagine that, Well, I'm sure the insurance company has heard of that. So the first question is the motion of an object rolling down an incline uniform motion? Is the velocity constant? Does it move at constant velocity?
Yeah.
No. It goes faster and faster and faster. The longer it rolls, it goes faster and faster and faster. The same thing here. How fast is this going the moment I let go of it? It isn't. Then it suddenly accelerates. This is definitely accelerated motion. Definitely. Which means we do not expect to get a straight line on a position versus time graph. And he doesn't. He doesn't. He does not get a straight line. This is position, this is time. He gets a curved line. And one thing that we notice is that by also using the incline, not only do you slow the motion down, but because it's moving slowly through the air, it eliminates the influence of the air. So the use of an incline slows the motion without changing its essential character, and it eliminates the effect of the air. So you can't get rid of the air, but you can at least study the situation where it's not going fast enough for the air to have an influence on it. This is difform motion. It's difform motion, absolutely. Well, that's not hard to see. You know it's going to be difform. What you don't expect is this. Is if you roll a marble down the incline and graph it, you get that. If you get a cannonball, which is much heavier, and you got to somehow get somebody to round that for you, what you find is that when you roll the cannonball down, yes, you get a curved line, but it is indistinguishable from the line for the marble. The cannonball does not roll any faster, even though it's many times heavier. They give the same graph. Holy cow. heavier objects don't roll faster. So the conclusion is heavier objects do not fall faster, which was what was taught by Aristotle. Now this is in the case of no air resistance. A case that violates this is a parachute. You open a parachute, you fall much more slowly than if the parachute remains in your pack, even though you have the same weight. That's because, will a parachute work on the moon when there's no air? No. No, you jump off. There are high mountains on the moon. You jump off of them with the parachute, you're just going to it's going to do no good. No. Can an airplane fly on the moon? An airplane? No. It's an airplane. There's no air on the moon. All right? You have to use jet engines or something to maneuver on the moon. So he finds that free fall motion is difform motion, but that heavier objects do not fall faster. Okay? More importantly, if he makes a graph of velocity versus time, not position, but velocity, since it's difform motion, can we get a straight horizontal line? No. The signature of uniform motion is a straight horizontal line. This is difform. It cannot be a horizontal line. But it is straight. It is straight. And whether he does the marble or the cannonball, the two motions are identical. The velocity definitely increases, but the velocity increases uniformly. So there is an acceleration. The acceleration is constant. For an object coming down an incline or free fall, the acceleration is constant and does not depend on the weight. Wow. If you measure it when it actually falls down, Galileo couldn't quite do that. He could extrapolate to it, but we can do it here. In fact, if you're in that measurement lab, you're probably going to do that experiment. You'll drop a ball and measure the position of the ball as time passes. You'll make a graph like this. The slope of the graph is the acceleration, and you'll get the acceleration due to gravity, which is the same for all objects. Now, in the metric system, it's 9.8 meters per second squared, which means nothing to you. Okay? I prefer, in this class, to talk about the acceleration due to gravity, or G, is constant regardless of the weight, not of gravity, due to gravity. And you need to know it, of course. It is 22 miles per hour per second. We call this little g. It means that if you drop an object, it accelerates downwards at 22 miles per hour per second of fall, regardless of whether it's a bowling ball or a crate or a cinder block or even a feather. If you get rid of the air resistance. NASA has a chamber 500 feet deep they can suck the air out of. Only NASA would have something like that. 500 feet's like unbelievable. And if you suck the air out of that and you drop an anvil and you drop a feather inside there with no air, they'll both hit the bottom at the same time. They'll both hit at exactly the same time. Now you fill it with air, the feather's going to fall a lot more slowly. But you saw me with the textbook here. I took my textbook in an earlier lesson and I put the piece of paper on it and I dropped it. The textbook removes the influence of the air on the feather of the paper so that it falls exactly the same as the book. Proof positive. But the quantitative value is 22 miles per hour per second. Now, the most difficult math you'll have on our exam is simple stuff. So, what if you fall for 2 seconds? If you fall for 2 seconds, you fall for a click and it's 2 seconds before you hit the floor, how fast are you going? Huh? 2 times 22 is what? 44 miles an hour. Is that going to cause some damage? Yeah. Oh yeah. Yeah. Stand up in your car, go under a bridge that's too low at 44 miles an hour and see what happens to you. What happens if you fall for just 1 second? What's 1 times 22? 22. What if you fall from this table? Now this table is, the height of this table is such that it takes about half of a second to hit the ground. So if you're in a bed this height, you roll off and you hit the floor, how fast are you going? If it's 22 miles per hour per second and you fall for half a second, how fast do you hit the ground? 11 miles per hour. Is that going to hurt? Absolutely. You ride a bike at 10 miles an hour, 11 miles an hour, you ride a bicycle under a bridge like this, it's going to hurt. Oh yeah, oh yeah. Can you hurt yourself in a 6-inch fall? Well, those of you, if you ever go to the ER, one of the most common things is people who walk down the stairs, they think they're on the last step, but there's one more, they don't cushion themselves, they come down hard, they fall 6 inches, and they break their ankle or break their foot. Very common emergency room injury. Okay? This is why humans are afraid of falling. You don't have to fall far to hurt yourself. We're terrified of heights. I am. Okay? I wasn't as a kid, but I am now. I was dumb as a kid, but now I know better. Okay? So you need to know this. Same regardless of weight. Regardless of weight. Regardless of weight. So that's one of the most important results that came out of Galileo's experiments. Now, there were several things that had to happen that we had to go through in order to get to the real final understanding of this. What we're going at is we're trying to understand motion here in the sublunar world. We've already found one of Aristotle's teachings false. That he said heavier objects fall faster. Galileo says no. They all accelerate at the same rate. But Galileo makes another claim, and he gets really close to the target. He misses it by a little bit, but he gets really close. He says, you know, if I build an incline that's really smooth and roll the ball down it, and then straighten it out gradually so that it's absolutely horizontal, he argues that if the ball were rolling and it went onto a horizontal surface, now that wasn't horizontal. He says that if I could make the ball smooth enough, and if I could make the incline smooth enough, the ball would never stop. The ball would roll forever. If you could eliminate the air friction, if you could eliminate the influence of the plank it was on, eliminate any friction, it would roll forever. What shape would it roll in?
In a circular shape?
Yes, it would roll in a circular shape. something that is horizontal, if continued for thousands of miles, would actually circle the Earth. And he gets all excited again. He says, oh my God, gosh, the natural state of motion is not a state of rest, which is what Aristotle said. He said it would roll forever in a circle. Circular motion at constant speed is natural motion. He concludes that a circular motion at constant speed is the ultimate state, is the natural state of any object. If you could eliminate all of the influences, then it would go in a circle. Wow. Aristotle said the ultimate state of any object is a state of rest. Galileo says, no. He says the object wants to keep going in a circle. If it doesn't, something is influencing it. He says objects stop because of friction. They stop because friction influences them and makes them stop. He says if you eliminate the friction, eliminate the air, eliminate any interactions here, the ball would roll forever in a circle. Wow. Wow. That's incredible. That is incredible. Turns out it's wrong. Now, the reason it's wrong is because the ball is being influenced. It's being influenced by the track. I know that because if I remove the track, the ball will not go horizontally. So it's being influenced by the track. It's also being influenced by something that he didn't think was there. He didn't understand, gravity. He did not understand gravity. Nobody understood the idea of gravity. But he was close. The only problem is the circularity. We are going to see, when we come now to Newton, that Newton says no. Newton says the natural state of motion of any object is constant speed in a straight line. The natural ultimate state of any object, according to Newton, is going to be constant speed, but in a straight line. If its speed changes, it's being influenced. If its direction changes, it's being influenced. Okay? So Galileo's really close in the early 1600s. He's really, really close. All right? He's very, very close. Any questions here? Any questions or comments? Well, the next person to come in is, I should say, of course, Isaac Newton. Isaac Newton comes in with a publication in 1687. But he's around in 1642 and so on and so forth. He's not, takes a while before he publishes this. But the story that I get is that Newton had established himself as a very competent scientist, Isaac Newton. Actually, it's Sir Isaac Newton. What's the Sir mean? What is that about? Yeah.
Like the old version of a PhD.
Not quite. Not quite. Not a PhD. It's not an educational degree. What is it? Who are modern Sirs? Well, Sir Elton John. And the equivalent for a woman is called a dame. In this country, you say, if you call somebody a dame, they get offended at that. But Maggie Smith is Professor McGonagall. It's Dame Maggie Smith. The lady who plays M in the James Bond is Dame something or other. Sir Elton John, Sir Ian McKellen, who Oh, he's in so many things. He plays Gandalf. A sir means you're knighted. You're knighted in the sense they put the sword on you and do this. It's the ultimate honor you can get in the British Commonwealth, in England, say. Okay? I'm very proud to say that a couple of my musical instruments in my arsenal of instruments were made by Sir Roger Bucknell. So his instruments are so good that he was knighted by who's the prince now out there? Not Prince George. Anyway, he was knighted. He was knighted. He got this letter in the mail. He talked about it on his website. He got this letter. It looks like a letter from the IRS. You know, it's a government-like looking letter, and you go, oh God, now what have I done? And he opens it up. He says, I've been knighted. Wow. Okay. He's knighted for his work ultimately. Now, the story that I hear is that he talked to Edmund Halley of Halley's Comet. And one of the things that they were looking at this time, which is the middle to latter part of the 1600s, was they started to think that Kepler was right and that the planets were orbiting the sun in ellipses. They started to believe that. They also had an idea that an object would go in a straight line unless it were influenced, which is Newton's first law. But, you know, it hadn't been completely substantiated. So if a planet were going around the sun, there had to be some sort of a tether keeping it tethered to the sun. There had to be some sort of an interaction between the two that would tend to pull them towards each other and keep the planet in its orbit. And the Royal Society had figured that in most cases forces depend on the separation of the objects. You know this if you have a refrigerator or magnet or two magnets, that the force is stronger when they're close together and weaker when they're further apart. You try and hang stuff on your fridge with a magnet, you put too much stuff on there, you separate the metal from the magnet and it gets weaker. So they suspected that this force depended on separation. And they went to Newton and said, what would be the mathematical form of that force? What would it have to be to make the planet go in an ellipse? What would the form of this attraction be? Some sort of an attraction across 93 million miles. How would this attraction change with distance such that the orbit would be an ellipse? He says, oh, what would be an inverse square? And Halley goes, how the hell do you know that? He says, I worked it out years ago. He worked it all out, you know, and stuffed it in a drawer and didn't think to publish it. Newton was a little weird. He was a definite true nerd, okay? He was afraid of people stealing his stuff. When Halley heard of this, he said, holy cow, no, you got to publish this. Well, what he did was in 1687, he publishes a book which in Latin is called Principia. Okay? A book on motion. The natural principles, the mathematical principles of natural philosophy. And just to give you an idea of the time he was in, we're sitting here terrified of the coronavirus. At least I am. I'm in the high-risk category. Do you know what the chances in London in like 1640 were of people dying from the bubonic plague? Does anybody know what the fatality rate was, what your chances were of making it through the next year? 50%. That means if I came back during the bubonic plague in London at its peak and came back a year later, half of you would be dead. Not to minimize the seriousness of what we have now. But back then, we didn't have medicine. We didn't understand how it traveled. They didn't understand what happened. And people were dying like hotcakes. They were gone. As always, the rich were the ones that survived by leaving London and going to the country. Okay? So he publishes this book called Principia. And it is axiomatic. it makes minimal assumptions. Makes minimal assumptions. You do have to make assumptions. You can't get away from that. But you minimize them. And then you prove everything from those basic assumptions. Mathematically. Prove everything from these basic assumptions. Mathematically, rigorously, you prove everything. You also carefully define everything. When you use a word, you say exactly what you mean by that word. We tend to throw words around and really don't clearly specify what we mean by the words. There will be a lot less misunderstanding if people would say, when I say this, this is what I mean. When I say this, I mean that. And when I say this, I mean this. And a couple of the things that he carefully defines are three fundamental quantities. He says, you know, if you're going to be talking about motion, what the hell do you actually measure when you measure motion? You got something moving, what kind of stuff can you actually measure? It turns out there are only three fundamental quantities. Everything else is made up of several of those measurements. His fundamental quantities. Carefully defines these. He realizes you measure time. And let me say this, these are absolute. His fundamental absolute quantities. Time, distance, and then the amount of inertia or stuff something has called its mass. The mass is the amount of stuff that something has in it. Okay? Distance, that's obvious. Time, we're talking about elapsed time, not whether it's 10:45 or something. We're talking about the time it takes from one thing to the next. That's what we call it, about time. If you measure how fast an object is moving, you measure how far it travels in what time. Distance and time yield velocity. Velocity is important, it's not fundamental. You want to measure acceleration. You have to measure velocity twice, distance and time twice, and then you have to measure the time between them again, and that gives you acceleration. So acceleration, though important, is not a fundamental quantity. It's a derived quantity. The fundamentals are only three: time, distance, and mass. And since we're talking about motion, we have to say, what quantity do we use to specify how much motion something has, and in what direction? The quantity of motion that an object has. Well, if you think about it, it depends on how big the object is. If you've got one SUV going 70 miles an hour, and then you have a car carrier carrying 8 SUVs on it, also going 70 miles an hour, which of the two has more motion, the car carrier or just the one car? Well, the car carrier. It's got 7 or 8 of those SUVs, all going 70. On the other hand, you can have something such as, it depends on if you have a car going 1 mile an hour versus a car going 70 miles an hour. The faster the car goes, the more motion it has. And so, the quantity of motion is called the momentum. And this is given the symbol P. with an arrow. That arrow means it is a vector. It has a direction. Motion has a direction. If you're standing out by the freeway and you say, oh my gosh, there's a truck going 70 miles an hour. Well, if the truck is going to pass you, you don't care about it. But if the truck is coming 70 miles an hour towards you, you do very much care about it. The direction of the motion is important. The momentum of an object depends on two things. The quantity of motion depends on two things. It is the mass of the object times its velocity. And it does depend on the direction. The velocity has a direction associated with it, so that is a vector. As an equation, we would say that P is equal to mv. Can you think of an object? So you can have, for instance, you can have an object going very slowly that has an incredible mass, that has a huge amount of momentum. Can you think of an object that's only going, oh hell, 1 mile an hour, and you could find one of these going 1 mile an hour that would have as much momentum as a train? What object out there going very slowly could have as much momentum as a train? What?
I was going to say train.
Okay, a train's got a hell of a lot of momentum. And a train going slow has got a lot of momentum, yes. But you could also have a train going very fast. This is why a train wreck can be just tremendous. Think of an object even bigger than a train that can be moving around. How about a cruise ship? A cruise ship is essentially a city on the water. If that baby comes in to the dock at even 1 mile an hour, it can rip up the dock. It has a huge mass, but it can be going very slowly. On the other hand, you can have a meteor, which is a small mass, going very fast, which can strike your car and put a hole in your car. So it's a combination of the mass and how fast it's going. That is what momentum is. And so here's where we're going to go. We'll kind of stop there. Newton, in Principia, states 3 laws. We'll pick them up next class. The first law essentially says this. He says, whatever momentum an object has, it does not want to change it. Once an object is moving, it does not want to stop, and it does not want to change the direction it's going. Something has to happen to cause the momentum to change. And that something we are going to call a net force. So look ahead in the book under chapter 3 on Newton's laws of motion, and also the law of gravity, and we'll be covering that on Monday. Have a great weekend and stay safe, okay? Bye-bye.